So today I'm going to be talking about Hall's marriage theorem. Some prerequisites for this lesson is you need to know some basic set theory and notation, and some basic graph theory. So first, let's talk about the definition, or what we're trying to find that Hall's marriage theorem helps us with. So we have some set X. It can have anything in it, but for simplicity, let's say set X has some numbers in it. For example, I don't know, 1, 3, 5, 8 or something. It could be any set. And then we have S is some set such that all elements of S, for all elements of S, S is a subset of X. So S is a set of subsets of X. And we want to know if there's some injective function f that goes from S to X such that f of S is an element of S. So what this means is that you choose one element from each subset, which is f of S, and all these elements combined create the entirety of the range, which is X. So as an example, if we, for our set X here, if we had the subsets 1, 3, 3, 5, 8, 3, 5, and 8, then we could say that f of this equals to 1, f of this equals 3, f of this equals 5, and f of this equals 8. And the union of these is going to be the entire set X, 1, 3, 5, 8 as desired. And Hall's marriage theorem gives us a necessary and sufficient condition for this. It says that such a function exists, if and only if for all W that is a subset of S, the size of W is at most the size of it's the number of elements in total in all the sets of W. So the union of all the sets in W. So this is what Hall's marriage theorem states, and this specifically is called the marriage condition. So next we're going to show a different interpretation of Hall's marriage theorem in graph theory instead of in set theory. And it's very easy to see that it's equivalent, so let's use this to get to the graph theory version. So for each element of S, let's make a node on the left side of a bipartite graph. So we have a bunch of nodes, and these are the elements of S. And then on the right side of a bipartite graph, we're going to have the elements of X. And then we're, so in our example, it's going to be 1, 3, 5, and 8. And then we're going to put an edge between some element of S and some element of X, if and only if these elements are, X is an element of S. So, edge between Si and Xi, if and only if xi's in Si. Okay? So we're going to add some edges based on these ones. So 1, 3, 3, 5, 8, 3, 5, and 8. 1, 3, 1, 3. Hopefully this is visible. 3, 5, 8. 3, 5, and 8. And we say such a function exists if and only if, or, well, yeah, if and only if there's some perfect matching, or some perfect, so we have some perfect S matching, or X matching rather, exists if and only if there exists a perfect, or an X perfect matching, I guess that's what it's called. If and only if there exists an X perfect matching, which is some matching that covers all the nodes of X. So in our example, some perfect X matching is this. This. It's very simple. We just have this matching here. And why does this mean that the function exists? Well, basically we just take f of s equals whatever it matches to. So I don't know, let's just call it xi. And that is if s is matched in the matching. If we have some other node of s that's not matched in the matching, then it can just equal anything in its equals any xi in s, because we already have the whole set of x covered. It doesn't matter what else we have, what the other values of the function are. So this is an equivalent formulation in graph theory, and yeah, now we're gonna talk about an example problem. So this problem is from the Canadian Math Olympiad in 2006. I believe it is problem 3. And the problem is in a rectangular array, of non-negative real numbers, with m rows and n columns, that's m rows and n columns. So first we get that each, well, I'll do it in bullet points, each row or column contains at least one positive element, and we also get that if a row and a column intersect in a positive element, then the sum of their elements are the same. So I'm going to say if x, y, using some kind of coordinate system, is positive, then sum of row x equals sum column y. And we want to prove that m equals n. So you may think this seems completely irrelevant from this whole Hall's marriage theorem thing that we've been talking about, but actually you just need to look at it in a little bit of a different way. So what we're going to do is we're going to create a bipartite graph again with the rows on one side. These are going to be the rows, and the columns on the other side, and we're going to connect them if they intersect at a positive element. So we're going to have some bipartite graph. And we're going to prove that there is always a matching, a row perfect matching. So I want to show always, there always exists a row perfect matching. And there also always exists a column perfect matching. And we just have to prove one of them because it's symmetric, of course. Symmetry. Okay, so we'll do it using contradiction. So let's assume, for the sake of contradiction, that there is no row perfect matching. And the reason we want to show this is that if there's a row perfect matching, it means there's a matching that includes every row. So that means the number of rows must be less than or equal to the number of columns. So how many rows are there? Is it m? M. So there's less rows less than or equal. M is less than or equal to n. And this gives us n less than or equal to m. And so if we have both of them, finally we get n to equal m. So that proving this proves this conjecture. So if there is no row perfect matching, then by Hall's there exists some subset of these rows. So I'll call it subset W again, which is a subset of X. Let's call the rows X and the columns Y, just like we did before, such that Hall's marriage condition is not satisfied. The size of W is greater than the size of all the neighbors of W, which is equivalent to what we had before. It's just the union of the neighbors of W, which is what we had originally. Okay. So let us find such a subset. So first, let's show that there exists a connected subset. Not just any subset, but a connected subset. So let's say we have some subset, right? We have some rows and we have some columns. And the rows connect to less columns than there are rows, like this. Well, if this subset is disconnected, for example, it's disconnected, we have something like this. Right, if it's disconnected, then there has to exist at least one of them, one of the connected subgraphs or subsets of this subset must also violate the lemma. If none of them violate the marriage condition, then the sum obviously doesn't, right? Because if for each connected subset we have less than or equal to, then if we sum over all of them, this inequality is going to remain, since they are disjoint because they're not connected. That's the whole point. Oops, this is supposed to have a sum. Therefore, there exists a connected subset that does not satisfy the marriage condition. And now we're going to strive for a contradiction using what we're given in the problem statement. So let's note that if some row and some column are connected, that means they have the same sum. Because, as we're given in the problem, if xy is positive, which is what we use to determine whether or not they're connected. So if they're connected, then the sum of the row equals the sum of the column. So if this graph is connected, all these rows and columns have the same sum. So all the rows and columns we're considering have the same sum. So let's call this sum k. So let me draw some subset here, for example, like this. Like so. This is some example. So now what we're going to do is maybe let's draw this grid, kind of. So we have some rows, more rows than columns. So let's note something, is that if the row and column intersected a positive element, they're connected. So that means all the positive elements of this row are in some of these columns here, right? Because this row connects to some of these columns. So only the ones that are in those columns can be positive. The rest of these must be 0. 0, 0, 0, 0, etc. These can be positive, the rest must be 0. And these ones can also be positive, and the rest must be 0. Right? But this is something interesting. Of course, they don't all have to be positive, since the graph doesn't need to be fully complete. But, so for example, this one could be 0, and this one could be positive. But anyway, if we sum all the columns combined, so if we take, for example, the sum of this column, the sum of this column, and we take the sum of the rows, we realize that they're the same because all the positive elements are in the intersection. So as we see here, if we sum the columns, we get all the x's. And if we sum the rows, we also get all the x's. So therefore, the sum of, I'll just call it row sum I over all I and w equals the sum of the column sum I for all I in nw. However, since all the sums are the same because it's connected, and we let it equal to k, so we have k times the size of w equals k times the size of nw. But since this does not satisfy marriage lemma, we have that the size of w is greater than the size of nw. And thus, we get k must be equal to 0. But this is a contradiction because all these sums are positive, because, as it says in the statement, the very last thing, each row/column contains at least one positive element. And then we are done. So yeah, that is Hall's marriage theorem and its application to a problem.